Okay, this is to give you an overview of applying a strain gauge for the class MEC 2960 at UMass Lowell. The setup I have here is as follows. So we'll use the solder iron later on. More importantly, what we're doing is we're installing a strain gauge. They come in packs of 5 or 10. And in that, on the back of the package, you'll see all of the relevant information, such as the resistance of the gauge. So here's one gauge that I've already pulled out that is still being protected, and we have a special tape that we use, and we use sometimes we'll use an acid, a low concentration acid, and then a neutralizer to neutralize that. And there's a catalyst that we'll be using that will be applied with adhesive, essentially super glue. We'll also have some swabs for cleaning, a flux for soldering, and protective tape so that we in the end don't remove unintentionally the wires. Today we're going to look at using a polycarbonate sample, and this was provided by the plastics department here at UMass Lowell. Its length is approximately 5 inches, and we have an 1/8 of an inch thickness. And with your verniers you can determine what the width is and all. However, I'm going to give you an approximation, and there's a reason behind this. It's essentially 1/2 inch, 1/8 inch by 5 inches long. Okay, so the first thing that I've already done is to clean the surface that you're working on. Because I'm dealing with chemicals, I'm using glue, and I have glasses on for safety reasons, as you should as well. So the gauge itself, in doing the application, is to adhere it to the region of the sample that you're looking to evaluate. So because we're putting this sample in Flexure, what we want to do is we want to put it at the midsection, and we want it properly aligned so that it's uniaxially or axially aligned along the length of the sample. Okay, so first what I want to do is use some sandpaper. The reason why I want to use a little sandpaper on the sample is to roughen up the surface. And I'll do so by simply sanding the surface in the region, being the center of the beam or the sample that I want to apply the gauge to. So that in turn changes the roughness of the surface. Second thing I want to do is, if I was looking at contaminated samples, maybe a metal sample, aluminum, whatnot, I would use a low concentration acid for cleaning it. These samples are not all that dirty, and for educational purposes I'm going to bypass that. There is a neutralizer that gets used after you would clean with the acid, but so all I'm going to do with that is put a little bit on the gauge, on the sample, and then I'll clean the sample off. And what they want you to do is to use the gauze, or you could be a Q-tip or whatnot, only in one direction so that you're not recontaminating the surface. Okay, at that point I'm ready to start aligning the gauge for its application. So here we have a uniaxial gauge, and it's sitting in a protective mylar, I think it's mylar, or plastic. I have tweezers that are clean. You'll note that there's two sides of the gauge. One's a dull looking side, and the other one is a more shinier side. What I want to do is remove the strain gauge with tweezers and put the dull side down against the sample. So I haven't put it exactly in the right position, and I'll show you a trick in a second. What I want to do is I want to pick this gauge back up, and I'll be using tape to do that. So this is a special release tape available from a number of suppliers, and all I'm going to do now is I'm actually just going to pick the sample up, or the strain gauge, I'm sorry. And the gauge is now floating around here on this piece of tape, and I'll go back for a second, put this over here. And what I can do, because I know I want this in the middle of the sample, is if I know it's 5 inches long, I'll adjust my vernier calipers until they are approximately at 2.5. And I can use this as a reference to tell me where approximately, by marking the sample, where the middle section is. The other thing I can do, if I know the sample is 1/2 inch thick, I can go to 1/4 of an inch. and then that gives me an indication of where the center of the sample is. So now I've kind of made 2 lines that tell me where I should put that gauge. Now what I want to do is grab that strain gauge again, and then I'm going to come from the top, and what I can do is align it with its grid marks. So every strain gauge has little marks on the end that tell you how it's aligned, so you can use that reference scratch that I put in the sample. There are times when you don't want to scratch the sample to cause a stress concentration. All right, so what I have now is I have the strain gauge just taped on the surface. What we want to do is we want to apply adhesive so that it stays there. We're going to use the following 2, glue and then a catalyst for that. So first thing we do is we open the catalyst up, and be careful, you know it's a chemical. You should have your safety glasses on, and you should wipe approximately 8 or 10 times the excess catalyst that's on there. I'm going to pull slowly back the strain gauge, and what you should be able to see is now I'm simply just going to go ahead and touch and wipe this catalyst on there. That catalyst is going to help the adhesive cure. So now I'm removing the cover. I have the adhesive. A little bit goes a long ways. So what I want to do now is I want to go ahead and just start put a small drop at the base of the gauge, and then I'm simply going to go ahead and slide that across. You can see from the darkness where the adhesive is. All right, so the next thing to do is to hold this down for approximately 1 minute. Okay, now I'm going to actually wait 1 more minute before I remove the adhesive tape. While I'm doing that, I can start to prepare for connecting wires that are going to be used to connect the strain gauge to the signal conditioner that you'll be using. So we have here 3 leads that are all in 1 wire. What you want to do is you want to separate and keep the black and white together, and then have the separate red as an independent lead. On the other side, you'll be doing the same thing. So here we have the red independent lead, and now we have the black and white leads that you're going to lead together. I'm going to take some wire strippers and simply remove the the covering of the wire on both ends. I've already done the red one on that side, so you want to, there's tricks of the trade, if you will. But I basically have a little bit of wire. That's all you really need that's being exposed. All right, so this wire right here is too small, so I'm going to actually use it up against here and pull that off. And now you can see that I have the wire stripped back. I'm going to turn these wires or twist them so that they're not frayed at the end. Don't be afraid, because they could cause a short. So I'm doing that on both of them. Okay, so we have now basically stripped the plastic coating off of the 2 ends of the wires, leaving the black and white as a twisted together pair on both ends, and then an independent red wire. I'm going to go back now to my strain gauge, so I've given that approximately 1 minute to sit. Most importantly here is that when you remove the tape, that you want to pull it back at 180 degrees. So you don't want to pull up, right? You don't want to shear that off. You want to basically have a low stress concentration on the gauge itself by pulling it back at 180 degrees. So now that I've done that, I have a little bit of trash that I'm going to put away properly. And you can see that I have the gauge attached to the center of the beam. All right, so next thing I need to do is to go ahead and solder the actual gauge to the wires. So here's a trick I'd like to show you. One is, you can use flux. You don't want to use too much flux, but basically that'll help you. And then this flux bottle, if you will, squeeze bottle, I'm just going to put a little bit on the end of each of the wires. Just, a little goes a long ways. All right, next thing I'm going to do is use my solder iron that's already been heated and solder that's provided, and I'll just touch this off. And all I want to do is just touch the portion of the wire that has been, the plastic's been removed on. And what you can see is real quickly, like, I've basically tinned the ends of these wires. And I'm going to do the same here. So there's plenty of solder on the solder iron. You don't want a lot. Okay. I'm going to put the solder iron back in its holder so it don't burn down the house. And now I'm going to take one of these ends and I'm going to go ahead and cut a little bit shorter. So it's maybe 1/8 of an inch long max. All right, and the next thing I need to do is to, I don't have to do it, but it's probably a good practice to go ahead and put just the smallest little drop on the pads of the strain gauge. Okay, so I've got a little bit of flux on each pad. These are two independent pads that are connected with the grid of the strain gauge. And as you would have already learned, essentially they allow you to measure the change in strain by actually looking at a change in resistance that's converted to voltage. All right, so now I got a little bit of solder on here, and I quickly just want to touch it off on the end of, or on the tab. If you put the solder gun on there too long, then you're going to have an issue with burning the sample. So again, I just want to touch it off. It looks like I'm going to need a little bit more solder. And that's a lot of solder. So a little bit is more than enough. Again, I don't want to hold it on there too long. And what I see now is either I don't have enough solder on there, or I could use a little bit more flux. Again. And now I'll just come in and touch it off. So effectively, I've just pre-tinned the end of the gauge. At this point, you'll take the pre-tinned ends, black and white together, and the red as an independent. Black and white will go on one side. And now that you put the solder on there already, all you have to do is come down and just touch it with some heat. And at this point, the black and white are attached to one end. As you see, the red wire wants to actually curl up, so this would be a good time for me to put my solder iron away and to go ahead and take the red wire and put a stress on it so it wants to stay in this orientation. And now what I can do is come back with the solder iron and just hit that. You keep it on there too long, you're going to melt the sample, and potentially you're going to melt the gauge and the sample. So you don't want to do that. So you would want to look at these under a microscope, well, under some magnification if needed. We have that at every station. And I'm just touching this off again. I just don't like the way it looked. That should do it. All right, now what I'm going to do is just take a little bit of simply masking tape, and I'm going to go ahead and attach the wires to the sample with that masking tape. And that simply is to generate a stress relief so that you don't rip the wires off of the sample. Okay, at this point, I'm really hoping that we have a good application of the strain gauge and the wires. So what we can do is we'll go to a multimeter now and we'll check its resistance to determine if this solder joint and these wires are good to go. Okay, now that we've put the gauge on and actually soldered the leads to the tabs on the sample, I need to bring to your attention that I made an error earlier. On this side you want the black and white wire together on the sample, and on this end you want 3 independent leads, and this helps us correct for compensation of thermal induced strain. Okay, so what I want to do is I want to check the gauge. The black and white are connected together there. The red is an independent lead. The way I do that is I'm going to use a multimeter. This meter basically is already powered up. It's showing me, because these leads are not connected, that I have an overload or I have a short or an open circuit. If I simply put them together, you'll see that I have very low resistance, so 0.0003 kilo ohms, which is a third of an ohm, which is a resistance associated with the actual cabling. So the the strain gauges were given to us. We should have a resistance of the gauge of approximately 120 ohms. And what I'll do to see whether or not the circuit is good, I connect the white to the red, which is actually going through the sample and the strain gauge, and I do in fact see up on the multimeter that I have 0.121, let's say, kilo ohms, or 120 ohms approximately. The other thing I can do is then go to the black wire. So now I'm black to red, and again I get the 1.120 kilo ohms. The other thing you could have done, just to make sure the blacks were connected together down at the end, is look for low resistance between those, and that's essentially 0. Okay. Now we know that this sample is actually gauges on there, and we have the dimensions of the sample, and all we're going to do now is wire these to your material testing platform. We're going to use the Mark 10 again, and off to the side of that we have a signal conditioning amplification that allows us to convert the change of resistance with the sample to a change in voltage. So I need to wire for wire into this, it's called a bridge completion module, and I'll do that using a screwdriver, which I have right here. All right, so it's just a quick color for color. So the first one I have is white. So I'll connect my white wire, and then the second one is black, and we'll connect that to the screw terminal. It doesn't have to be all that tight, but just snug. And now I have my red, and I'm connecting to the screw terminal that's connected to the bridge completion module up here. So it's red for red, black for black, white for white. Okay, at that point in time, what I could do is I could take the leads from the multimeter, and I'm going to go ahead and attach those to the output from the bridge completion module and the signal conditioner, which has some amplification in it. Okay, so I have the red being the output from the bridge completion module and signal conditioner, and the black basically going up to the multimeter. And I had it on resistance, but now what you want to record is voltage DC. So you can see here I have approximately 13 point, whatever it is, 4 millivolts DC. I can change the scale, or negative 0.0137 or 8. If I took the sample and I distort it a little bit, then you can see that as I strain it, the output voltage varies or changes. Again, I strain it, the output voltage will change. So the negative value is a bias. All right, if I keep pushing it, then this should, as you see here, looks like I get continuity backwards. which doesn't really matter. You're looking for the differential. So I have a negative 0.0, let's say 17, and then as I deform it, it's going to change to negative 0.053 approximately. So you're looking for that differential voltage. Finally, as a check, before we do a Flexure test, it would be to, with a known radius that you can measure, apply the sample to the surface of it and then push down on it. And now we have a known bending radius, if you will. And you could look at the output voltage. Now you've got a negative 0.055, let's say. In the unstressed condition, again, I go down to that bias value. So you're looking for the differential. There's your strained sample, bent at that radius, output voltage in volts, I'm sorry. Right, and then the unstrained sample. And that value should go back approximately to the same value. However, you may plastically distort or plastically deform the sample, so it may not go all the way back, or you could have drift. So that's that portion. And now we'll set up for a Flexure test. Okay, so now that we have the gauge wired to the signal conditioner and we can record the output voltage from the gauge that is on the sample, that being polycarbonate again, we want to make note of, for this 3-point Flexure test, we want to make note of the support length from nose to nose, and you can measure that or use a vernier caliper, whatever you find is appropriate. So a 3-point Flexure is just that. So I have one support nose, another support nose, this compliance to those or they'll roll, and then I have the loading nose here. So again, you're going to need to know that distance and the geometry of the sample. You're also going to have to potentially adjust the dial indicator such that when the sample is being touched, you zero it out or you have a reference point. The Mark 10 load cell you're already familiar with from your tensile testing, and that dial indicator need to be adjusted as necessary. So I have basically a bias there on the load, so I can remove that bias, turning that down to 0. And approximately, we'll find out once we put the sample in, whether or not we need to adjust the dial indicator. So I don't want to load the strain gauge itself. What I want to do is I want to invert the sample, and I want to then, I'm going to remove the wire a little bit here so it's not going to be in my way. And here's where you want to take a little bit of time and make sure that you have your sample with the strain gauge centered on the load nose. Okay, I'm going to bring this the load nose down a little bit just so I can kind of nest the sample so it's not moving. And I may have a slight deformation on that. I do have a bias now of about approximately 0.4 pounds. And what I can do is, with the dial indicator, is I can go ahead and adjust where it starts by moving this down. I'll tighten that up. And now we can zero that dial indicator. And you see as the sample goes down, it's going to go ahead and deflect the dial indicator. The dial indicator has 1,000th of an inch, 0.001 or 1,000th of an inch resolution. Looks like the load cell has about 1/10 of a pound resolution. And the multimeter is showing us a bias. In this particular case, it's negative 0.023 approximately. All right, at this point, you may want to double check everything, but we're ready to go. Your procedure states that you should acquire 15 points, as I understand. So I'm just going to go ahead and make sure I'm cranking in the right direction. And we're going down. We can see the load coming up. You can see the voltage changing, and we can see that I've put approximately 0.025 inches of deformation on the sample. I have a load on it, and I have steady, basically, output voltage. And I'll go ahead and get another point, recording the load, the output voltage from the strain gauge, and the deformation. So I think that's 0.050. 2.2 pounds and minus 0.038. You'll repeat the process. 3.4 pounds, 0.080 inches of deformation, and an output voltage of a negative 0.048 approximately. Again, we'll repeat the process. Load, deformation, 1 revolution, which is approximately 1/10 of an inch, and the output voltage. 5.6 pounds, deformation, output voltage, and you repeat the process. And for each one of these, you'll be recording those 3 measurements. And if we actually, with your iPhone or your phone, Droid or what have you, you could be recording a video of this and then try to pull that those data points off your video. All right, so after you get your 15 points, what you can do is simply unload the sample. And things are looking pretty good here. So I'm going to say my final point is 11.6 pounds. I haven't been keeping track of that. That's your job. You need to keep track of that. Looks like I have about a negative 0.14 or 142 volts. And I can bring this load off of the sample. It should go approximately down to 0. And if I'm just touching the sample again, I should be approximately at my start point. And then you can compare your bias at the beginning of the test to that of what you see now with the load removed. Keeping in mind that we had a little preload of about 0.4 pounds. And that concludes the 3-point Flexure test here at UMass Lowell, MEC 2960.